All right, so welcome back. So, section 3, chapter 11, this is the part B. And I had mentioned in previous videos that the idea of direction, when in 2D, right, in a plane, the idea of a slope is very helpful to think about the direction a vector is headed. But in space, right, like if you take a look at vector v here, the concept of slope loses its luster because you have to ask with respect to what, right? So you would have to think about it. There's three different directions here. We have the x axis, the y axis, the z axis, and to even discuss the angle. Again, you have to question with respect to what, right? So it makes the vector definitely makes an angle, but an angle with respect to what? And what you're going to see is that vectors in space, in order to actually have three angles that are of importance. So we label the angles, alpha, beta, gamma, and each angle has its own, axis from which it's with respect to. So, for example, alpha, right here, is the angle from the x-axis to the vector. And then the beta would be the angle from the y-axis to the vector. And finally, the gamma would be the angle from the z-axis to the vector. So you can see that you have three different angles. And these angles are what's referred to as direction angles. So there's two concepts you're about to see. You're about to see the idea of how do we find direction angles, and then the other concept is what we call directional cosines. So we'll start with directional cosines, and then it's very simple to get from directional cosines to directional angles. So what we do is just quite simply, going back to our alternative form of our dot product, you can see that this formula is built on around the vectors u and v. But we've already discussed that the I, j, I put z, let me write that as k. The I, j, k notation that you're used to, right, when you're discussing vectors in engineering and physics, each of these is itself a vector. It is what we call a basis vector, which tells it also we know that they're unit vectors. So, for example, the I is defined in space as the vector 1, 0, 0. So I can get you to your directional cosines fairly quickly. All I have to do is, instead of discussing a vector u dot v, let's just assume for a second that the two vectors that are of interest to us is going to be one of the directional vectors, say I and then v, right? So all that's going to happen right now is I'm going to substitute, instead of having a vector u, I'm going to use the vector I. And I would do the same thing with j and same thing with k, only that I don't think I need to go through all of that. I think I can get you to it fairly quickly. So let me write it. Let's just assume that I were to substitute, and I would now have v dot I, right? So instead of vector u, we'll have this vector I. And that would now be defined as the magnitude of v times the magnitude of I, multiplied by cosine of, we are told that the angle between I and the vector is what we're going to refer to as alpha. So cosine of alpha. All right, well, we can get to this fairly simply. What is, for example, what is the magnitude of I? Well, we know that's 1. Right, so we end up with V dot I is equal to the magnitude of V cosine of alpha. Only if you were to go through and dot this out, I'm trying to save time, but I also don't want to I also don't want to lose sight of what we're trying to do. So vector v, as you recall, we just normally use components like v sub 1, v sub 2, v sub 3. Now, can you see that if I were to dot these two vectors, can you see that you would only be left with a v sub 1? I want to see if you can spot that before I do it, right? It would be 1 times v sub 1 plus 0 times v sub 2 times 0 plus 0 times v sub 3. So the v sub 2 would 0 out, the v sub 3 would 0 out, and 1 times v sub 1 is just v sub 1. So I hope it makes sense to you that I can simply replace v dot I with v sub 1. Or the dot product of those two would just be v sub 1. All right, and right now let me go ahead and get you to what we call our directional cosines. So if I just solve the above for cosine of alpha, I get cosine of alpha is equal to what? It's equal to v sub 1 divided by the magnitude of v. And in fact, I think I will spare us from doing the same thing with j and k, and I will just go ahead and get us right to your the rest of the directional cosine. So that therefore cosine of beta would just be v sub 2 over the magnitude of v. And finally, cosine of gamma would be equal to v sub 3 over the magnitude of v. All right. All of these refer to your directional cosines. So you might be asked to find the directional cosines. And to do so, you just note that you would have 3 different answers here. And these would be your directional cosines. You also might be asked to find your directional angles. And in that case, you start with your directional cosines, and then you're just going to to find the angles, you just have to take cosine inverse of each. So let's go ahead and do both on this next example. So it says find the directional cosines and angles, so we want both, for the following vector. And show that, we can show that this identity holds true, but let's start with the directional cosines and directional angles. Okay, well, let's go ahead and let me see if I can lost track of my little sheet here. Entertain yourself for just a second. There we go. All right, so let's start. So I'm going to go ahead and write my directional cosines out. So that would be cosine of alpha is equal to v sub 1 over magnitude of v. Cosine of beta is equal to v sub 2 over magnitude of v. And finally, cosine of gamma is equal to v sub 3 over magnitude of v. So clearly, in each of these scenarios, I'm going to need to know the magnitude of v, so we should start there. So the magnitude of v is going to be the square root, and let's just go down the line, so that's going to be 2 squared plus 3 squared plus 4 squared, right, which is just the square root of 29. So that's equal to the square root of 29. All right, and now what about v sub 1, v sub 2, v sub 3? Well, this is easy enough. just understand that we're given the vector in ijk notation, but we can quickly go to component form, right? That's just 2, 3, 4. In that case, as you recall, this is your v sub 1, this is your v sub 2, and this is your v sub 3. So we now have everything that we need. We're just going to plug in v sub 2, v2 in for v sub 1, and divide it by the magnitude. And we're going to do the same thing for cosine of beta and cosine of gamma. So we'll go ahead and do that really quickly. So what is the answers? So here is the answer to the first part of the question. Cosine of alpha is going to be 2 over the square root of 29. Cosine of beta is 3 over the square root of 29. And cosine of gamma is 4 over the square root of 29. So, okay, so we're done with the directional cosines. And now we want the directional angles. So in this case, we actually want to, what is alpha, what is beta, what is gamma? And simple enough, it's just, all we have to do is take the inverse, cosine inverse of 2 over the square root of 29, the inverse of 3 over the square root of 29, and the inverse, cosine inverse of 4 over the square root of 29. All right, and we might as well just go ahead and just round a little bit. So I'm getting an alpha of roughly 68.2 degrees, a beta of roughly 56.1 degrees, and a gamma of roughly 42 degrees. All right, and now all of this is pointless unless we can understand the geometry, right? So here's your vector, and now you are just able to find the angle from from the x-axis, the y-axis, the z-axis to your vector. That's exactly what you just did. And these are your directional angles. Finally, it's fairly simple to show, I'm not even going to do it, it's fairly simple to show that this relationship holds. All that you know what cosine of alpha is, right? So you would just plug this in, square it, plug this in here and square it, and plug this in here and square it. And then you would just take the sum of those squares. And you would end up with 29 over 29, which is 1. Okay, so this next part of, last part of our material that we need to know is not easy for, how do I want to put this? It's not always easy for students to grasp, and let me do my best. So, for example, if we were looking at, we have a boat on some type of ramp, and it looks like it's getting ready to be placed into the water or pulled out of the water, and in the previous sections, we would have two vectors, and we would be asking questions like, what is the sum of those two vectors, right? We would be asking questions like, what is the resultant of those two vectors? Only now you can think of it as, what if we just have the resultant, right? Like, we know for this boat, we know the force due to gravity that this boat is applying here, right? So, but we want to start to decompose rather than compose. We want to decompose this force into two other forces, the sum of which equals F. So the idea is, just starting with F, force due to gravity, can we decompose that into two other vectors whose sum is F? And this is what we mean by what they refer to as vector projections and vector components. So without a lot of elaboration, I'm first of all, I'm not a physicist. My background is in applied mathematics. I say that disclaimer so that if I make a silly mistake or language mistake, we can just, well, it's my get out of jail free card, right? Because I'm not a physicist, so what can you expect, right? Okay, so let's take a look at how we're going to think about this. So first off, let's get out of this f and w sub 1, w sub 2. Let's just think of it as two different vectors, right? So we have vector v and we have vector u. And we're interested in two scenarios. So scenario 1 is when the angle between the two vectors is some type of acute angle, right? Less than 90 degrees, larger than 0. And we're also interested in when the angle between the two vectors is obtuse, so greater than 90, less than 180. And now, what we're going to do is we're going to think about how you would decompose these u, all right? And let me see if I can do my best here to draw what I'm trying to say. So I'll use the same notation, w sub 1, w sub 2, but I'm going to decompose. So let's start with the acute. All right, so what would w sub 2 look like? Well, w sub 2 would look like this. And what would w sub 1 look like? Well, w sub 1 would look like this. So this here would be w sub 1, and this would be w sub 2. Let's do the same thing if that angle were obtuse. All right, so in this case, w sub 2, we would be would take on the following form, and then w sub 1 would take on the following form. Okay. And now let's actually give these a name, right? So let's actually give a name to this vector w sub 1 and vector w sub 2. And then after we give them a name, we'll start to look at some properties. So let's start with w sub 1 is what we refer to as the projection of vector u onto vector v. All right, so I'll in just a second I'll tell you how we denote that, but right now let's define it. Okay, w sub 2 would be referred to as the vector component of u orthogonal to v. All right. So I mentioned at the onset that this can be slightly dense or a slightly hard topic to grasp for many students. It might not be the case with you, but nevertheless, for many this is hard to grasp. So let's not lose sight of the goal. I mean, if you don't mind, let me paint a picture. Let's assume that this is a refrigerator. I have a refrigerator at my house. And I ask you to come by and help me move a refrigerator. So both you and I are pushing up against this, we're pushing some force up against this refrigerator, and it's moving. Well, if it's moving, I might know the total force that's being applied, right? I know that the refrigerator is moving. But maybe I'm trying to figure out how much of the work am I doing versus how much of the work are you doing? Does that make sense? Now, does it also, while we're here, does it also make sense to you that, let's say that it's awkward in that we're both trying to get our hands on this refrigerator and either push or pull it, and let's say simply due to the position that you can only get your hands at some angle like this when you're pushing, right? Does it make sense that that angle at which you place your hands is going to affect how much of the work is being done by you, right? So in other words, if you could put all of your force directly horizontal versus if you were reaching way up here. So maybe try to keep that in mind as we work through this so you can understand the goal of what's happening here. So I said what I was going to do. I was going to define these two vectors, and now let's go ahead and show you some properties. And these are the properties that come out of this. Well, first off, vector u is the sum of w sub 1 and w sub 2, right? So that is the decomposing part. We decomposed vector u into two different vectors, which we call w1 and w2, okay? Let's also go a little bit farther, and let's notice some things here. So let's notice that w sub 1, so take a look here, see how w sub 1 is parallel to v, right? You can spot that. Definitely scalar multiple of v. There's some multiple scalar out there that I could multiply v and get it out here, right? So another property, w sub 1 is parallel to v. Also, w sub 2, let's take a look at w sub 2. W sub 2 is, in each case, is orthogonal to v. Now I'm just going to use this little symbol here, perpendicular, but orthogonal to v. All right, at this stage, I've defined these two vectors. I've given you some properties of these two vectors. And the last thing I want to do is show you how we denote these two vectors, right? So this is the notation we use. So we would say w sub 1, the way we would write that, the notation would be, I'll write it and then I'll pronounce it for you. All right, and we refer to this again as the projection of u onto v, right? If you were to ask me to why do they use the word projection? Can you imagine? Do me a favor. Just look at this. What my style is here. Can you imagine if you had a sun up here shining light, and you were to look at the shadow that was produced here? That might help you think about the projection, right? Let's go ahead and go to how do we denote w sub 2. And it's fairly simple. It's just going to be vector u minus vector w sub 1. Makes perfect sense if you were to solve for w sub 2. So I'll just go ahead and tell you the hardest part is always going to be finding the projection. That's going to, it's not hard, but it's the majority of the work is going to go into here. Once you have the projection, it's very easy to find the vector component. All right, well, let's, no more discussion. We have everything we need. If my handwriting wasn't great, I have both of those. Everything that I wrote is here as well. Let's go ahead and go to an example. So example 5. So we're asked to find the vector component of u that is orthogonal to v given that, all right, so that's interesting. So this is actually a lot easier of a question. So here, let's start with what we're given. So we're defining u as the following vector, and we're defining v as the following vector. And in this case, we're actually told that w sub 1, right, which is the projection of u onto v, it was 8, 6. So this is quite simply, this is trivial at this point. What you're asked to find is you're asked to find the vector component. So in other words, you're asked to find w sub 2. So let's start. W sub 2 is equal to u minus w sub 1. And I have w sub 1 and I have u, so I'm just substituting in. And this is just simple arithmetic from here. All right, so w sub 2 in this case is negative 3, 4. So all of that work to find this vector right here. Okay, let's go to the next example. So what I will do, with your permission, and I don't think you'll object too much, but I won't show you the proof of where this comes from, although it truly is not that hard to do. It just slightly labor intensive enough that I normally do it in a classroom setting, but I won't do it in a video setting. So let me read what we're looking at here. So the projection using the dot product. So there's another application, right, of the dot product. So we begin with some assumptions that we have these two vectors, u and v, and they're not zero vectors. Okay, they're non-zero vectors. All right, so then the projection of u onto v. In other words, w sub 1 is you can reach the projection of u onto v by taking the dot product of u and v divided by the magnitude of v squared multiplied by the vector v itself. And I offer this to you without proof. If you are interested in the proof, then just come see me during office hours and I will show you. Ready? So let's read example 6. It says find the projection of u onto v, right? So this is what we're looking for. And the vector component. So we want both w sub 1 and w sub 2. And this is the information that we're given. All right, let's start with w sub 1. The projection of u onto v. All right, well, obviously what we're going to need is, let's come off to the side, we're going to need the dot product, u dot v. We're going to need the magnitude of v squared. So let's go ahead and get this out of the way. So let's see. So we got the dot product of u dot v and the magnitude v. If you don't mind, I've already done dot products with you. I've already done magnitudes with you. So I'm just going to go ahead and give you those answers. So u dot v is equal to 12. And the magnitude of v squared is 54. So this ends up being 12 over 54 multiplied by, and I'll just keep the ij notation, so multiplied by v, which is 7i plus j minus 2k. All right, so W sub 1 is simply equal to, what do you got? 12 times 14 over, no, 12 times 7 over 54. So I'm going to go ahead and, this is going to be in reduced form. So 14 ninths I plus 2 ninths J minus 4 ninths K. Okay, so all done. So I found the dot product, I found the magnitude of v squared, and I've then just distributed that onto vector v, and there we go. So now we have w sub 1. Finally, w sub 2 is simple enough. It's just going to be vector u minus w sub 1. So that's going to be 3i minus 5j plus 2k minus 14 ninths I plus 2 ninths j. I'm running out of room. Minus 4 ninths k. All right, and the result of our arithmetic is 13 ninths I minus 47 ninths j plus 22 ninths k. So there is w sub 2. Okay. So enough with the theory. Let's actually look at an application of some of this work, and let's see if this diagram is enough to help you. So the application that we're going to look at is the idea of what's called work, right? So let's start with the definition. So we say the work, which we're going to use W, the work done by a constant force, F, as its point of application moves along the vector P to Q, is one of the following. So, in other words, let's take a look at how we define work. So, notice that first let's look at P to Q. So can you agree that this box was started at point P and we moved it from point P to point Q, right? So that's what we mean by this part here. That's just a distance. And the F in this case is just the force that was used along that line of motion. So you could think about work as is equal to force multiplied by distance. And I like that definition, force multiplied by distance. But again, that assumes something. That assumes that just like I was talking to you about the refrigerator, right? If you can get all of your force along the line of motion, right? So if you can, if you're trying to push a refrigerator and you can put all of your force this direction along the line of motion, well, that makes life a lot simpler if we're trying to figure out how much work is being done. But sometimes, right? Sometimes that's not possible. Sometimes you might have to have an angle, especially if you have two people, right? You can imagine the first person might be able to push up against the refrigerator like this, but the person behind that individual might be pushing at an angle. Now that angle here affects both our formula, and it affects how much work is being done. So in this particular case, notice that if there's an angle involved, this is your definition of work. And I'll go ahead and expand on that really quickly. So let's see if we can, let's see if we can expand on it through an example. All right, so this will be the last example for this section as well as this video. Let me read. So it says to close a sliding door, a person pulls on a rope with a constant force of 50 pounds. Right? So there's in other words, you're trying to close this barn door, and you have a rope that you're pulling on at a constant force of 50 pounds, and then you got an angle of 60 degrees. Now our job is to find the work done in moving the barn door 12 feet, because you got to move this door 12 feet in order for the barn to close. Okay. Let's see. Let's go ahead and start with our definition. So work is what we defined as the magnitude of the projection of that force on to that directed line segment P to Q. And that's going to be multiplied by the magnitude of P to Q. Okay, so since our individual is not applying all of the force along the line of motion, since there is an angle here, we're going to have to account for that angle. And I hope that I'm not skipping too much when I jump right to it. So that's going to be the same thing as cosine of the angle times the magnitude of the force times the distance, P to Q. So this becomes our new formula. I'm going to scoot back a second. So this is our formula, and that is a dot product, by the way. This is our formula when there's no angle being accounted for, but if there is an angle, you need to change it up. So this becomes our formula here. So, okay, and so now let's just finish this up. This is fairly simple. So cosine of, this is going to be cosine of 60 degrees multiplied by, how much force was it? 50 pounds. And that's going to be, ended up being times that distance of 12. So that's just a half times 50 times 12. That's 300. I assume that would be referred to as foot-pounds. Okay, so you've seen dot product. It just started off with something innocent as, you know, multiplying, how to multiply two vectors, but we've gone from multiplying two vectors to how to find angles between vectors to directional angles, directional cosines, all the way up to applications in physics for finding work, all using the dot product. All right, I will conclude, and I will see you guys in the next video.